Very good morning once again to everybody. Our next is related with recent development in biodiesel production technology, because ultimately biofuel play a very important role, and in this regard I will tell about the recent developments related in biodiesel production technologies. My talk consists of motivation, and then I will talk about the feedstock, what is the scenario at national level and at international level. Besides this one, I will discuss about the conventional methods for biodiesel production, and then the recent developments related with process intensive techniques, case studies which we have done in our laboratories, and in which the design of experiments play a very important role. Then what are the environmental concerns related with the present techniques of biodiesel production, and the algae is one of the most important source as far as the biodiesel production is concerned. We will talk about at the end, and finally we will talk about the conclusions of recent developments of biodiesel production techniques. As we know that as far as the motivation is concerned, we are always concerned about the global energy, which is almost can say we are huge amount of fossil fuels we are consuming, and they are finite, and therefore the sources of fossil fuels are depleting. And due to that reason, there is a change in climate and a huge amount of harmful emissions, including greenhouse gases and various other things are there. They are emitting in the atmosphere. Biodiesel is one of the source which we can call it as under the category of sustainable renewable energy source, and it can give us energy security. It can reduce greenhouse gas emissions, and it can be produced from renewable energy sources, because with every crop it can be renewed. And besides this one, it has an economic impact. And one of the reasons that here I would like to tell you that in the case of developed world, they have excess edible oil. So their focus is on converting this excess edible oil into biodiesel. The same case is not applicable in countries like India, developing countries like India, where we have a scarcity of edible oil. In that case, we cannot convert edible oil into biodiesel. Fortunately, we have large resources of this non-edible oil, and more than 500 species are available in our country. Those non-edible oil species can be converted into this biodiesel. So our focus will be the conversion of non-edible oil into biodiesel. Besides this one, waste cooking oil is also available in abundance, and this can also be converted into biodiesel. So these are the main sources, and if you just look at in terms of percentage, the vegetable oil percentage is 79%, non-edible oil percent is around say, which includes biomass based upon 6%, 12% is for non-edible oil, and 3% jatropha one can use it. So this resource of non-edible oil, we have to focus and do the innovative research to convert into biodiesel. If you look at this particular graphics, you will see that in the beginning of 1860, most of the this biomass was the traditional biomass was the main consumption, and only the utilization of coal started in 1880, and slowly it has got peak in at the beginning of 1920, and finally you can say the era of oil, natural gas, this NGL and gas has come. So the point is that maximum peak was in 1980s to 2000, where conventional energy source was consumed in a very huge quantity. Traditional biomass contribution due to traditional biomass has decreased, but the recent trends after in this particular century, after 2000, you will see that oil and gas starts reducing, coal starts reducing, and besides this one, you will see that renewable energy consumption is increasing. The total consumption of renewable energy around say next decade, almost we can see that it is quite comparable as compared to the conventional energy sources. And in the near future, almost renewable energy source will play a very important role. As you know that if you use a conventional energy sources, environmental degradation is a main can say drawback of conventional energy sources. The sources for the case of burning fossil fuels are coal, oil, gasoline, diesel, natural gas. All these after the combustion they produces the emissions. Emission consists of NOx, sulfur dioxides, then carbon dioxide, methane, particulate matters, toxics. All these emissions have a severe impact on the atmospheric issues, which causes climate change, smog, acid rains, hazardous air pollutants, and various other things. And due to that reason, there is an impact on not only human beings, on animals and crops also. So therefore, this environmental degradation has become a big issue in this century, and our objective is that we have to use renewable energy sources in such a way that environmental degradation should be minimized. Since in our country, as far as the automobiles are concerned, we use petrol and diesel. In most of the other developed world, consumption of petrol and diesel is almost equal, 1:1 ratio they are consuming. But in our country, the gasoline demand, gasoline that is the petrol, it is used in cars and other four-wheelers, whereas diesel is used in the case of trucks. Though the number of trucks are less as compared to cars, but the total consumption of diesel is very high as compared to gasoline. And you will see that the data up to 2011-12, and even the recent data I have not included, the consumption of diesel is around 5 to 6 times higher as compared to the petrol. So therefore, a slight change in diesel price will have a severe impact on our economy, whereas change in petrol price will not affect much. So therefore, ours is a typical special case where substitute for diesel is important as compared to petrol. Of course, for petrol, people are substituting by means of ethanol, but in the case of diesel, we can substitute by means of biodiesel. So substitute of biodiesel from economy point of view, which is more important because our consumption of diesel is 5 to 6 times higher as compared to the petrol. So this is a unique problem our country is facing. As far as the feedstock sources are concerned, at national level and international level, the country which is having excess of that source, they are consuming that oil into biodiesel. Palm oil is available in abundance in Malaysia. European Union rapeseed oil is in excess. Soybean is in excess in USA. Sunflower in Argentina. Jatropha, that is a non-edible oil, which is in India. And in Philippines, coconut oil is in excess. And the data related to oil yield, that is the number of tons per hectare per year, this data varies. Palm oil it is highest 3.93, whereas in the case of coconut it is 0.66 tons of coconut oil per hectare per year. Other conventional feedstocks, mahua and palm, karanja, tobacco seeds, almost can say fundamentally any oil, whether it is a vegetable oil or non-edible oil, it can be easily converted into biodiesel, principally. So the point is that whatever the source available, localized source available, one should try to convert that oil into biodiesel, rather than focusing on one or two type of species, which is not good for the long-term impact as far as the nature is concerned. The non-conventional feedstocks, which is in our country, they are not very popular. Lard, tallow, poultry fat, fish oil, bacteria, algae, microalgae. These are the almost non-conventional feedstocks, but they are experts says that they are very important from future point of view. Now this is a very important data. Main feedstock, which consists of edible oil. Since edible oil is in excess in China and European countries, so they are focusing on that one. So out of, you can say around the total in terms of seeds, in one seed you can acquire around say 300 grams to 400 grams of oil after extraction. So therefore, if you just look at, in that case, edible oil, coconut gives around a very high quality of oil content, 63 to 65%. Whereas in jatropha and other neem oils, around say 20 to 30% or 40% one can get the oil. Castor oil, you can get 53% out of seeds. Out of other sources, the most important one is the microalgae, where almost 30 to 70% you can say you can get the oil from the raw material. So these are the different oil content based upon the weight basis available in the literature. In Rajasthan and Gujarat, one of the important source is the Citrulus colocynthis, that is popularly known as thumba. So these seeds are separated from the fruit, and then it can the oil can be abstracted from the seeds, and this oil can also be easily converted to biodiesel. This particular this thumba, it has some anti-inflammatory drug. It can be used by farmers. It can be used by cattle feeds. Flowers are some medicinal values are there. So likewise, you can say it has some other applications also. And normally, you can say at present, if it is not used for biodiesel, in that case, it is sold to the soap industry, which is purchasing in abundance. In normally, this particular these seeds are known as Indrayan in Hindi and bitter apple in English. With these sources, now I am going to discuss the conventional methods or conventional techniques through which we can produce the biodiesel. This technique, almost you can say, even more than 100 years back it was known, but at that time the price of petroleum was not very high. So due to that reason, much development has not taken place, because at that time per gallon petrol price was quite small. So due to that reason, people have more focused on internal combustion engines. But the technique was available even at that time, even in South Africa. In conventional method, what happens? There is a mixture of oil, alcohol, mostly because alcohol, it is a methyl alcohol we are using. People say that it is a green process, but the objection is that if you use a methyl alcohol, in that case, it is again a petroleum product, and therefore this process cannot be called as a totally green process, 100% green process. In that case, if you use a biomethanol, which is produced through green process, then we can call it as a 100% green process. Otherwise, you have to use other process, for example, say ethyl alcohol or other things. If you use it, then we can call it as a 100% green process. The catalyst, based upon the percentage basis, weight percentage you can take, may be homogeneous. Most of the at present homogeneous catalysts are the most popular, but at research level, the heterogeneous catalyst people are working. So this mixture of raw oil, alcohol and catalyst is added in a reactor, and then a stirrer is there at the center portion, and through this stirrer continuous mixing takes place, and finally the immiscible layer between the alcohol and the oil, the immiscible layer breaks, and then the this methyl ester heavy molecules are converted to smaller molecules in terms of biodiesel. And finally, we can get a biodiesel, and as a byproduct, we are getting the glycerol. So around say 10 to 20% we are getting the glycerol, and then we are getting the biodiesel. After washing and separation, we can get the final product of biodiesel, which is giving up to 90% of the yield. This is the most conventional technique. Maybe the reactor varies from small half liter to up to say 100 liters, 200 liters, commercially available. And most of the commercial reactors are based upon this technique. In terms of ratios and weight ratios, say roughly around say 100 kg triglycerides or any that is triglyceride means any vegetable oil, raw material oil we can take, and if you mix it with 10 kg of alcohol, this particular reaction is based upon stoichiometric ratio. Normally, alcohol is taken double the stoichiometric ratio, so that the reaction can be always in the forward direction. It cannot be in the reverse direction. If the reaction takes place in the reverse direction, soap formation will take place. The chemically correct ratio point of view, we can get 100 kg, we can convert into 100 kg of biodiesel, means 100% conversion. And besides this one, 10 kg we can get glycerin, which is a byproduct. And this particular byproduct has a very high calorific value, and it can be used as a fuel also. If you look at the chemical formula, in that case, the fat or oil triglycerides, they reacts with 3 moles of methanol, and finally the outcome we are getting glycerol plus FAME, fatty acid methyl esters. this fatty acid methyl ester is the biodiesel we are getting after the reaction. Now this reaction, if you are using in conventional reactors, mechanical reactors or mechanical stirrers, in that case it requires a huge amount of time. Maybe sometimes it is more than 1 hour. So the point is that the conventional technique has a drawback where energy consumption is high, time requirement is high, and besides the suppression process is not environmental friendly. Various issues are there where almost this catalyst is considered to be a pollutant, and water washing also creates a trouble, and therefore the new methods are required to find out to reduce the time, environmental friendly process, as well as less energy consumption. This is from chemistry point of view. A triglycerides reacts with 3-methanol in the presence of a catalyst, and it will get glycerol plus biodiesel. So glycerol always as a byproduct when you use this oil plus methyl alcohol in the presence of catalyst, maybe this is a basic catalyst, that is potassium hydroxide or sodium hydroxide. In that case, in the product side we have always glycerol plus biodiesel. So glycerol as a byproduct we always getting. In terms of plant point of view or as a block diagram point of view, let us say an example of karanja oil. If it is mixed with alcohol in the presence of KOH, we are getting biodiesel, unrefined biodiesel, and glycerol. And then after the removal of excess, normally you can say instead of 3:1, we add excess alcohol. The excess alcohol after the reaction, it has to be separated so that it can be again utilized for next cycle. So once the alcohol is removed, then we can get alcohol-free biodiesel, and then it is washed with water. So after the washed water, even it is also played a pollutant role, and it erodes the land. So therefore, this is, if a big power plant is there, a big biodiesel plant is there, then again it is a how to tackle with that one have to think. Then biodiesel, after removing the wastewater, we can get the biodiesel with without moisture, with moisture, and then after heating we can remove the moisture. And finally, the neat biodiesel, B100 means it is now a pure biodiesel. Once it is mixed with the diesel, how much fraction it is mixed, based upon we can call B10, B20. B10 means 10% biodiesel, 90% diesel. B100 means 100% biodiesel and 0% diesel. And this once this B100, we can directly use compression ignition engines, where almost can say people say that up to 30%, if you add it to the diesel, there is no need of any change in the design of the engine itself. Almost the same performance you can get it by using the CI engines. As I have told you, there are certain challenges faced by conventional techniques. In the raw feedstock in oil, the main important variation is the FFA content, means free fatty acid content. If this content is less, say less than 2% or 3%, then in the presence of alkali, alkali catalyst, reaction can take very fast. But if FFA content is high, in that case, sometimes the soap formation take place, and reaction there are difficulties in reaction to achieve the product of biodiesel. So therefore, in that case, what happens? Two-step reactions are followed, where first the FFA content is reduced, and then in the presence of alkali catalyst, this biodiesel conversion will take place. Besides this one, we have to take care that water should not be present inside the raw material or raw oil, because once the water is available, in that case, what will happen? The saponification will take place, and the oil will be converted to soap, and this is anti-reaction of biodiesel. Besides this, as I have told you, washing is a big problem. So therefore, removal of residual triglycerides and glycerol from the product is important. Then only that standard biodiesel we can get it, and which matches with the standards available in the literature. Of course, once the glycerin is a byproduct, there is difficulty in complete conversion, and besides this one, wastewater is a pollutant. So these are the main difficulties associated with conventional. Of course, most of the processes are by means of these conventional technologies, but these are the difficulties associated with this one. So meaning is that there is a scope for development of new process which consumes less time, which saves the time. Highly efficient means they consume less input power, and besides this one, the process should be environmental friendly. All these requirements can be fulfilled by couple of new recently developed techniques. Before I discuss about the recently developed techniques, which are known as non-conventional techniques, I would like to classify the biodiesel process intensification. A conventional method I have already discussed, which includes mechanical steering. Now, drawbacks also we have discussed. Now, recently, last 1 decade, the most of the focus is on non-conventional methods, which includes ultrasonic methods, microwave methods, hydrodynamic cavitation, and sometimes the hybrid methods means combination of any of the two techniques, ultrasonic plus microwave, or maybe ultrasound plus hydrodynamic. And these are the techniques, ultrasound, microwave, and hydrodynamic. These techniques will, in which the reaction will take place at atmospheric conditions, slightly above atmospheric conditions, whereas in supercritical method, the techniques, this reaction takes place at very high temperature and pressure. So therefore, industrial viability is a question mark. But the advantage in the case of supercritical technique is that catalyst is absent. So catalyst is a big nuisance, and therefore, if it is absent, due to that reason, main attraction in supercritical process is that without catalyst, the reaction can take place. So we will discuss one by one these non-conventional methods and what are the status in the literature. Process intensive techniques, the meaning is that PI is the term used to describe the strategy of reducing the size of the chemical plant needed to achieve a given production objective. Means if a plant is efficient, the size will automatically reduce. Any chemical engineering development that leads to substantially smaller, cleaner, and more energy efficient technique is called as process intensive. That is the main objective from chemical point of view, that a process can be efficient if the size is reduced, time consumption less, and environmental friendly process must be there. So with this objective, almost the focus in the case of PI techniques are that reaction time should be less, conversion rate or yield must be high. Most of the cases, in the case of conventional reactors, the ratio is 1:6, means twice the alcohol you have to use. Of course, it can be recovered, but still you can say the total cost will increase. So if it is less than the, say, as compared to the conventional and conventional techniques, if less molar ratio is used, that is always welcome. Then the low catalyst, as I have told you, catalyst is a creates a pollutant. So therefore, this homogeneous catalyst, if you use less percentage, it is always welcome. Total lower operating cost and energy consumption, this is also focus. Besides this one, now people are focusing on, instead of batch production, now people also focus on continuous production and separation of reaction products. Recovery of glycerol, catalyst, and excess alcohol is also important. And besides this one, we know that feedstock, any feed, because once you develop a process should have a capability that it should respond according to the feedstock nature. So feedstock flexibility must be there. So in that case, flexibility means whatever the variation in FFA content is there, the same process should accommodate and give the biodiesel as per the standard requirement. That is a very important challenge as far as the design is concerned. And besides this one, the overall impact on the environment should be as minimal as possible. Now, in those PI techniques, one important PI technique is ultrasound cavitation. This is from last 1 decade. Ultrasound has a huge amount of applications in chemical industry. The concept, this particular earlier it was used for to mix the two immiscible oils, and later on it was thought that it can also be used for the case of transacidification reaction to produce the biodiesel. In this particular principle, in this process, as you see in the right hand side diagram, due to ultrasound waves, very small thin micron level bubbles are formed. So therefore, the stages are that formation of the bubbles, then is growth of the bubbles, and then the collapse of the bubbles. Due to these three mechanisms, what happens? The mixing of alcohol with oil will take very fast, and the transitive reaction will get the biodiesel in a very fast way. Further, in this particular process, we can get high flame yield, which is around, which is expected to be 96%, and we can get it in 30 minutes. Remember that time is a very important factor. You consume more time means you are consuming more energy. In the conventional reactors, the time requirement is around say 1 to 1.5 hours, or sometimes it is 2 hours. Whereas in this case, same yield and quantity of biodiesel you can get it in less than 30 minutes. That means we can save energy. Time point of view, it's a good one. Plus total energy consumption point of view, it's a good one. And plus performance quality of the biodiesel is quite good quality. So this is an efficient method for crude oil with because FFA content is high. So ultrasound, almost Japanese and other countries, a lot of work has been done, and at a research level, this ultrasound is considered to be a potential candidate for production of biodiesel. These are some of the diagrams and principles in which the ultrasound reactor works. There are two categories of ultrasound reactors. One is horn type, another is the bath type. The right-hand side diagram represents the horn type of reactor, which is the horn is submerged inside the oil plus alcohol reactor, and when the ultrasound waves passes through the liquid, then the layer between the alcohol and liquid will break, and then the biodiesel conversion reaction will take place. For controlling purpose, the water bath is there outside, and whatever the alcohol it is evaporated, that is condensed in a condenser. Bottom portion almost say a simple 50 watt machine is there, where around say 50 ml to 100 ml as a laboratory purpose. For experimental purpose, this machine can be utilized. Right hand side consists of, you can say, bath type, where you can see that inside the bath we have put a flask and a small quantity of below the bottom surface you can say transducers are there, and those transducers will produce the ultrasound waves, and due to this ultrasound waves the mixing of biodiesel will take place. Normally, Japanese scientists has proved that frequency of irradiation between the range of 28 to 40 kilohertz. In this frequency, whatever the alcohol and oil mixture is there, they will be converted into biodiesel. Above this frequency doesn't have impact, as well as the less than 28 kilohertz frequency also doesn't have any impact for mixing. This is the range of frequency where easily you can convert the oil plus alcohol mixture into biodiesel. These are the experimental data we have achieved when you compare the yield of this yield with respect to yield of ultrasound and yield of mechanical stirrers. This is for a molar ratio of 4.5:1, means 4.5 is the alcohol and 1 is the ratio for the case of this oil. You'll see that yield is above 90% as compared to mechanical stirrer. Mechanical stirrer less than 80%, less than 90%, whereas in ultrasound it is more than 90%. The yield is clearly higher as compared to the conventional mechanical stirring method as compared to ultrasound. Besides this one, you see that there is a drastic reduction in the time. For same conditions, in the case of conventional stirrer, the time requirement is 40 to 45 minutes. Whereas in the case of ultrasound, within 15 to 20 minutes, you can get the transcription reaction. Means a time saving is there, plus at the same time, you can save the time, and you can get a good quality of biodiesel. So different cases it is there for 0.5 catalyst percentage, 0.75 catalyst percentage, and for 1% catalyst percentage. We see that almost you can say within less than 10 minutes you can get the biodiesel, whereas in conventional process around 35 minutes it will be required. So almost 7 times reduction in time in the case of ultrasound as compared to the mechanical stirring. That is almost can say a severe, huge amount of saving of time is there. This is a typical 100-liter capacity which we have produced in Delhi Technological University, and at a time we can produce 100 liters of biodiesel. Normally, you can see in earlier diagram it was a batch production. At one time you can produce it, and then you have to remove that particular raw material, and then again you have to add some fresh material. So that's why it's a batch production. People are also focusing on a commercial level in the United States. This ultrasound cavitation reactors are also available in a continuous type, where almost you can say feedstock is added with the alcohol and mixed with this particular portion, and then the ultrasound reactor is there. Due to ultrasound waves, the mixing here will take place, and it will go through this path, and then in this column almost you can say separation of biodiesel will take place. So biodiesel through centrifuge, it is converted into, because the glycerol and biodiesel have different molecules, molecular weight. So by centrifuge, biodiesel is separated from glycerols, and then biodiesel is supplied to the application purpose, and glycerol is again collected and it can be used for its own applications. So this is, in this process, this is a continuous type process, unlike the batch production. The present status, almost you can say, ultrasound assisted transfication. This process, ultrasound cavitation, is very successful in enhancing the mixing of reactants with either homogeneous or heterogeneous catalyst, leading to significant reduction in reaction time. As I have told you, the reduction in reaction time is very significant as compared to biodiesel conversions using conventional transfication. Still, a lot of work has been done in the case of this ultrasound, but the majority of the research studies carried out so far focus on parametric and optimization investigations, with a number also studying catalyst leaching and reusability as well as biodiesel quality. Now, catalyst, if you use a homogeneous, you have to throw it away. If you use heterogeneous catalyst, you can separate it, but very few studies using heterogeneous catalyst is available. Number of research papers, you can say, by industry or by faculty, it is available. But the point is that notably limited attempts have been made to elucidate the mechanistic features as well as the underlying physics and kinetics of the ultrasound. Ultrasound, once the product is there, people can say, but what is the mechanism behind that one? Still, it is not very well known. And particularly when you use a heterogeneous catalyst, the total mechanism, justification for mechanism and logic is still not available in the literature. So therefore, this can be treated as this offers as an opportunity for future work in this area to advance the current level of knowledge and understanding. On the whole, the current ultrasound assisted biodiesel production technology status remains largely at bench scale, means only at laboratory level, at just for experimental purpose people have designed the plant, but at pilot scale project still only a few case studies are available in the literature. So therefore, conversion from laboratory to commercial level still requires some work to be done. To bridge the gap between the large scale commercialization, several areas worthy of future investigation includes continuous ultrasound reactor systems, especially using heterogeneous catalysts. Because heterogeneous catalysts, the important thing is that they can be reused. The cost of catalyst can be saved. And pilot scale test as well as techno-economic feasibility one have to find out. So therefore, economic aspects again play a very important role. Just like ultrasound cavitation, the principle of hydrodynamic cavitation is also same. Whenever a high pressure liquid passes through a hole, it comes out in the form of a jet. Once it comes out from the form of a jet, it is in the atmospheric conditions. So how the pressure varies inside, suppose this is a hole through which a high pressure fluid passing through that one. So a vena contractor is formed, and on this vena contractor the pressure is equal to atmospheric pressure. So once here it comes out from the orifice, then the pressure will drastically reduce, lower than the atmosphere, and finally the pressure will again come to atmospheric conditions. So cavitation, in this particular hydrodynamic cavitation, the vaporization takes place due to bubble generation, bubble growth, and bubble collapse. These three simultaneous things takes place. Due to that reason, what happens? The mixing becomes very fast. And this particular system has a scalable quantity, means you can just, whatever the laboratory system, if you design a particular process, you can scale it at a bigger size. Whereas in ultrasound, the scaling is again an issue. This is a typical hydrodynamic cavitation reactor. This particular schematic diagram is taken from UCT, Bombay, where they have worked on various types of oils, and the total capacity of the pump was 1.5 watt. Here, this is a storage tank. Through this particular valve, it is supplied to the pump, and through the pump, it is supplied in a pressurized condition. It is supplied to the orifice, and after the downstream side of the orifice, again it is added here. The continuous circulation converts the oil plus methanol into biodiesel, and that can be separated once the specified time is circulated. So here we can use a pump of 1.5 watt. Pump is the main device for energy dissipation. Suction side is connected to bottom of the tank. Discharge from pump is divided into two branches. This is just for different, how much is the pressure. Based upon the pressure is a variable. Based upon this variable, we can just note down the performance of the system itself. Operator temperature is below boiling point of methanol by circulating water. Means we have to keep the temperature below 80 degree. Otherwise, what will happen? The methanol will evaporate. Because evaporation of methanol is around say 65 degree or 70 degree. So one cannot cross through 65 or 70. This is a diagram related with our hydrodynamic cavitation reactors, which in Delhi Technological University we have manufactured, and in the Renewable Energy Journal we have published a paper. You can find out the diagram, and this is the photograph of the diagram where through this tank the suction side it is supplied to the pump, and then pump compresses the liquid and it passes through the orifice. Once it passes through the orifice, the mixture comes out in the form of a spray, and the cavitation conditions are formed. And due to cavitation conditions, the mixing takes place very fast. So that is the thing. In this case, a vertical chamber is there, and the water portion, the pump is not shown here. Here the pump is fitted, and through that pump, again it is supplied in a pressurized condition to this pipe, and continuous circulation will take place. So based upon this one, easily one can convert into, because this particular hydrodynamic cavitation has good scaling qualities, and due to this good scaling qualities, biodiesel production is very, very fast. Another important technology is the microwave technology. We are all familiar that microwave is an integral part of our kitchen. So the same principle, same microwave, or with slight modifications, the same microwave can also be applied for biodiesel production also. It is a very highly efficient heating method, and main advantage in that case is that there is a reduction in reaction time, and yield improvement is there, and due to its simplicity and low cost and energy economy, it is a very popular method. Whenever an ultrasound, this microwave is generated, in that case, alcohol molecules are polarized and they are at par with the magnetic field generated by microwave. So due to polarity in the case of alcohol molecules, they very fast react with the alcohol, with the oil, and biodiesel conversion is quite fast as compared to other techniques. So because of the effective heat transfer, processes with microwave irradiation can be completed in a much shorter time than those with conventional heating. The reaction rate of microwave assisted reaction increases drastically, which reduces the reaction time. So here the main focus by using this PI technique of microwave and other things is that reaction time can be reduced. And due to reduction in reaction time, less energy will be consumed, and at the same time the process will be environmental friendly. Again, a diagram of microwave reactors where almost you can say inside you can put a sample is there, and the sample by applying the microwaves, you can convert the sample oil plus alcohol mixture into biodiesel. So FAME yields are achieved by homogeneously and heterogeneously acid catalyst classification under microwave radiation. So observing the results obtained in literature, it is concluded that the rate of energy consumption to biodiesel generation would be decreased significantly as compared to other process. Here in microwave also, the energy requirement is very, very small, and therefore what are the product we are getting is a good quality product and also comparable with the conventional methods. Now, I have discussed about ultrasound, I have discussed about the microwave. Now, a couple of experts have worked in the hybrid reactors, where they have clubbed the two reactors, because each system has its own advantages and certain drawbacks. So they have tried with hydrodynamic cavitation with ultrasound. Here in this portion, this particular cavitation circuit is this one complete, and here in this case the ultrasound is also there. It is a ultrasound horn is put in the upstream side, where upstream side of the nozzle of a hydrodynamic cavitation. Whenever the pressure is high, in that case ultrasound efficiency improves, because in that case mixing will be very fast. So here the upstream side of this hydrodynamic cavitation, the pressure is high, and if you insert ultrasound horn, in that case, the effectiveness of the mixing will be improved, and biodiesel production can be converted very fast. This hybrid reactor can give better results as compared to individual ultrasound and individual hydrodynamic cavitation. So that's why people are working in the case of hybrid type of reactors. Besides this one of the experimentalists, he has worked in the case of combination of ultrasound and microwave. Here, this is a reactor. This is a photograph of that one. In this, at the center portion, and from the bottom portion, it is ultrasound is coming, and through the side portion, it is microwave is coming. So when mixing of these two, when the frequency of these two, ultrasound and microwave, superimpose each other, their effectiveness is they are very, very highly effective. In that case, almost hybrid reactors with a minimal amount of time, one can get the biodiesel with the raw material as oil and alcohol in the presence of catalyst. Another important, of course, it is a developing stage, reactive distillation column, where almost you can say distillation column is a chemical engineer's forte. In that case, the different, almost you can say the plates are there. So on these plates, this oil plus alcohol mixture passes, and it has a zigzag path, and through this zigzag path, finally it can convert into biodiesel. This kind of process is also Professor Kiss from Europe. They are working in that particular area. Besides this one, we are having a membrane reactor, where membrane reactor, what happens through the membrane, almost can say membrane is a very small can say size membrane is there, where only biodiesel molecules can pass through that one, and the other triglycerides etc. remain inside that one. But again, the conversion factor is very small, and it is only research level. Otherwise, the cost will be very high. So till now, whatever the process we have discussed, those processes have drawbacks, because in each and every process we are using the catalyst. Of course, microwave, ultrasound, and hydrodynamic cavitation we can use less as compared to the mechanical string. But still, there are certain drawbacks. What are those drawbacks? Because the point is that in the case of catalyst route, treatment of FFA, because if it is high percentage of FFA is there, first we have to reduce that content, and then you can use the catalyst. Besides this one, if water is present, you cannot get the reaction. In that case, the negative reaction will take place, and the oil will be converted to soap. Therefore, water is detrimental. Catalyst is consumed if it is a homogeneous catalyst. In that case, again, it is a big issue. And then the point is that ultimately, once the biodiesel is formed, we have to remove catalyst stresses from waste produced, low glycerin purity, and generation of wastewater. So all these are the drawbacks if you follow a catalyst route. But the advantage is that at low temperature, around say 50 to 60 degrees centigrade, with atmospheric conditions, we can achieve it. The advantage is this one. Drawback is that if you use a catalyst, then there is a problem. So people, researchers particularly find out that instead of homogeneous catalyst, if you use a heterogeneous acid or alkali catalyst, which are through natural resources, so they can nullify the effect of homogeneous catalyst. So in that case, heterogeneous catalyst, what happens? They can be recycled again, reused several times, and suppression for the product is quite easier and better suppression, and minimizing material and processing cost, and further the process development environmental friendly. Besides this one, with heterogeneous catalyst, one can go for batch production or continuous production, and finally the purification steps are also reduced in that case. This is the complete diagram of catalyst, which is almost as a homogeneous catalyst, enzyme catalyst, heterogeneous catalyst, which is almost a recent phenomena. Last 5 years, people have started working in this area, and in the case of heterogeneous catalyst, new recent developments are solid nano catalyst they are using, which has a very high impact and reactivity with the reaction will take place very fast, and then the sodium titanic nanotubes also using at the nano level. The main issue is that heterogeneous catalysts has its own importance, and people are working because it will become a big business. If you produce a very good catalyst, in that case, the reaction time will be very small, and at the same time, the process can be environmental friendly. So this is the brief idea regarding the different weightage is given to the catalyst, and people are following the different path. But here, our objective almost can say homogeneous catalyst, well known, but it is almost can say it creates a lot of problems. And mixture of it is mixed and it cannot be recovered. Whereas heterogeneous catalyst, different methods are there where it can be easily recovered. Till now, the process which I have discussed is based upon that once you extract the oil from the seeds, and that oil can be reacted with the alcohol and the catalyst. Now, this process almost can say gums and other can say impurities are also added with the oil. So people thought that why not we can go for some innovative process that is called as in situ transfiguration process. In that case, there is no need to remove the oil from the seeds. Seeds itself is mixed with the alcohol, and through the alcohol, through the seeds, only the biodiesel will be coming out. In that case, almost the advantage is that gumming were reduced, and around 98% of in situ transfiguration can be achieved. Both the extraction and gumming were reduced. In situ transfiguration is otherwise known as reactive extraction, where the extraction oil takes place along with the transfiguration of oil and biodiesel. So this is almost a recent phenomenon, and quality of biodiesel is very good because normally conventional methods, this viscosity is high in that case as compared to the standards, and to reduce the viscosity, this kind of methods can play an important role, and the final product can be within the standards available in the literature. So in situ process eliminates the expensive costs that are employed for extraction oil. In situ transfiguration can be used for any kind of oil seeds and feedstocks. Now, the process till now I have discussed is that in that case you have to go through the catalyst route, and catalyst has its own certain drawbacks. So to avoid that conditions, without catalyst, if you don't want to use a catalyst, in that case the only path available at present is the supercritical withdrawal process. In that case, we don't use the catalyst, and at laboratory purpose, we to test, to convert the oil with the alcohol, we use autoclave, and in this autoclave, high temperature and pressure is generated. And once the high pressure and temperature is generated, the raw oil is converted into biodiesel, and then it is separated and it's collected. So compared to the catalytic process, purification of product is much simpler and more environment friendly. But the drawback is that temperature and pressure is high. Let us see that how much quantity we are using. This is called as supercritical process because supercritical conditions are generated at high temperature and pressure. So say for example oil and fats with methyl alcohol, if it is mixed, and this is a supercritical reactor. So in supercritical methanol reactor, temperature is around 350 and 20 megapascal means 200 bar pressure is generated. Now product is good, but the point is that conditions are stringent, and due to these conditions what happens, they are not industrially viable, because to generate 350 degrees centigrade and 200 bars, it is just like a boiler. So the cost will be suddenly very, very high. Otherwise, product point of view, it is the best one. Biodiesel you can get it with very good quality, and glycerol also good quality you can get it. So glycerol always, in this process, glycerol is always a byproduct, just like a catalyst route. So advantage in this supercritical process is that you can get the product without adding the catalyst. But the point is that the price where you have to pay is that temperature 350 degrees centigrade and 200 this bar. This high pressure and temperature condition is the limitations for this particular process. So these are the diagrams which are shown. You can use an autoclave with 50 ml, 200 or sometimes 250 ml sample size one can use to convert raw oil into biodiesel. Now, people have worked in this area also. In the case of supercritical methanol process, they have converted, since as I have told you that this supercritical methanol process, very good process, no catalyst is required. Now the point is that industry point of view, now the main focus is that how to reduce the stringent conditions, operating conditions, means temperature and pressure should also be lower. So one of the method which is followed is, you can say, we can use a co-solvent, because co-solvent has a wide range of applications in a chemical industry, whereby using the co-solvent they will not take part into the cycle or a reaction, but at the same time the stringent pressure conditions, pressure and temperature conditions can be reduced, just like a reactor, just like a catalyst. So here this particular apparatus is there, almost 250 liter size of autoclave is there, and in this autoclave, once the oil plus alcohol is added, afterwards you can say the CO2 is added to create a pressure. In this case, what is the advantage? Advantage is that you can get the biodiesel with low pressure and temperature conditions as compared to the earlier. Earlier it was 200 bars and 350 degrees centigrade. Now the optimum condition is 280 degrees centigrade, which is less than 300, quite achievable, commercially achievable, and the molar ratio is 24, and 98% of yield of methyl esters you can achieve it. And this condition, almost time requirement is only in 10 minutes you can get it, right? And reaction pressure is 14.3 3 megapascal, or you can say 143 bar, whereas earlier it was 200 bars. So overall, you can say by using a co-solvent, you can reduce the stringent conditions of supercritical conditions or low temperature pressure. You can achieve a better results. People have tried with many other type of co-solvents, nitrogen as well as other gases they also use. So depending upon that which co-solvent you use, the results will differ. Now, this slide is almost, you can say, this is almost the last 5 years people are working. As I have told you that there are two products. Biodiesel is the main product and glycerol is the byproduct. Now in the Europe, etc., what happens? The production of biodiesel is quite high. So therefore, as a byproduct, the heaps of glycerols they are produced and utilization of glycerol is not much. So the point is that what to do with the glycerol, it is a big question in the European countries. And Germany also, they have reduced the production of biodiesel due to this reason that what to do with the glycerol. So a new development has taken place, and this is called as Saka's process, where Saka was a scientist from Japan. Instead of methyl alcohol, he has used methyl acetate. Methyl, this particular, you can say, methyl alcohol mixed with acetic acid, it can be converted into methyl acetate. So now methyl acetate is mixed with oil and fat, and then the supercritical conditions are at 350 degrees centigrade and 20 megapascal when the reaction takes place. In that case, what happens? If you just look at the reaction, triglycerides with 3 moles of methyl acetate, that is chemical correct ratio, we can get the FAME. FAME is nothing but biodiesel. Besides this one, now instead of glycerol, we are getting triacetylene. Triacetylene is an additive which is normally added with the fuel. So therefore, this is applicable, or you can say presence of triacetylene is good to improve the properties of the fuel. So in that case, you will see that we have nullified, almost can say, now we have nullified the production of glycerol or glycerin. So due to that reason, most of the cases now in the future, almost research are focusing on this reaction. Instead of methyl alcohol, now you can use methyl acetate, and by using the methyl acetate, the product will be FAME, methyl esters, fatty acid methyl esters, and triglycerides will be there. The triglyceride acts as additives, and additives are always welcomed in the presence is welcomed in the fuel. So main feature of this slide is that glycerol is absent, and this gives you quite relief. Recently, I would just like to tell you that in the case of this other techniques, till now the techniques which I have discussed, in those techniques we are using catalyst, and without catalyst, high temperature pressure conditions are generated. Recently, a Brazilian studies has shown that corona is a form of plasma. If plasma passes through the mixture, in that case, what happens? The reaction takes place very fast. Plasma itself takes part as a reactant. In that case, even at low temperature plasma, normally you can say in Gandhinagar, the IPR, Institute of Plasma Research Center is there. So they are expert in the case of plasma, and we are having a collaboration with them to produce biodiesel using the plasma as a catalyst. So in that case, plasma, what happens? The condition of high temperature pressure is also reduced. So therefore, plasma technique can play a very important role in the future, where without catalyst, we can apply this technique at low temperature and pressure, atmospheric conditions, no high temperature, no high pressure. So this can be considered to be ideal conditions in biodiesel production, where at low temperature and pressure, in the presence of plasma, triglycerides reacts with the methanol, it will produce biodiesel plus water. That is the main advantage. When the water is present in the early reactions, it will not give the biodiesel. But in that case, what happens? Even the water is present, the triglyceride will react with the methanol. in the presence of this plasma, corona type of plasma, and you can get the biodiesel plus H2. So this is almost a breakthrough as far as the biodiesel production is concerned, and with very less time you can produce it. But only a preliminary study is how the reaction takes place, and besides this one, what is the mechanism of that one, this is still to be investigated. So this is a typical diagram used by Brazilian study, that is corona flow is there, where almost 2 electrodes are there, internal electrode, and outside it is almost, can say, spiral shaped external electrode is there. In between a glass tube is there, in which the gas plus argon gas, this gas means argon gas as a neutral gas, it is passed, and sample inlet, the oil is passed, and between the 2 electrodes the plasma is generated, which acts as a catalyst to provide a reaction between alcohol and the oil itself. So this is considered to be the latest study as far as the biodiesel is concerned, and plasma can play. Plasma application is already there in the case of waste management, solid waste fuels, etc. It is there, but in the case of liquid fuels, the first time this study is available, and only a preliminary level studies are available. Here I would just like to tell you that since glycerol is a byproduct of our conventional techniques, so plasma can also play a role to convert glycerol into synthesis gas, CO plus H2. So plasma has a wide range of applications, and by proper applications of plasma, you can convert this biodiesel and this glycerol into synthesis gas, which can directly be, synthesis gas consists of carbon monoxide and hydrogen, and this is considered to be an input or a raw fuel for fuel cell or any other application, or for example, say Fischer-Tropsch method, where this can be converted to liquid fuels. So this particular composition is good for the case of various chemical processes. Now I will tell you that whatever the case studies we have done, how to do the experiments for the case of microwave, ultrasound, and various PI techniques, process intensive techniques. Normally the choices available is that optimization of microwave, normally this particular process we call it as optimization of the techniques, that at what optimum conditions we get the results. Normally you can say at present QH is the most popular catalyst. As compared to that one, what is the heterogeneous catalyst we can take? Heterogeneous catalyst, it is we can say that we can use beryllium oxide, which is quite expensive, calcium oxide less expensive but less effective, and besides this strontium oxide is also there. So out of those catalyst, heterogeneous catalysts, anyone we can select it. Besides this one, our optimizing process parameters are time, catalyst weight, and methanol to oil ratio. 3:1 is the chemically correct ratio, and actual process what happens, we have to use both. So we can vary these things. Besides this one, materials are waste cooking oil. We have used methanol and CO2 from available from the market, and we have used Samsung 28 domestic microwave oven, which is normally used for household purposes, and wattage are 900 watt. Now in this case, what happens? The total is the laboratory. The biodiesel production process is this one. This waste cooking oil mixed with methanol and catalyst. It is put in the microwave, and then after microwave, this once the reaction takes place, then the washing takes place. Washing and separation takes place, and at the bottom the glycerol is separated, and then the biodiesel, this is shown by yellow color, is separated in the, and then the sample is supplied to the GCMS, this gas chromatography, and where biological analysis is done, and then we can find out, okay, what is the yield available achieved. So these are the steps in the laboratory. We have to go through that one to find out the actual data through the experiments. Now, design of experiments is a very, very important aspect in biodiesel. Not just by, you cannot say that by 1 or 2 observations the biodiesel is produced. A scientific way we have to do the design of experiments, and recently almost most of the papers, the design of experiment is an integral part. Say for example, total power supplied was 180 watt. It's a constant in all the experiments. We have to consider the factors. Factors means there are almost 3 factors are there. This oil to alcohol ratio x1, one factor, catalyst percentage another factor, and time requirement is the third factor. So on these 3 factors the final yields depends. Now these factors have the different levels. 0 represents the central level. Okay, from past experience we know that answer comes nearby, and plus how much variation is there. So -1 level is the lower side and +1 is the higher side. So with this range, normally these ranges are based upon past experience. So sometimes experiment has to be done randomly, and then we have to decide those ranges. So 3 levels, 3 factor, this is there. And if you go for a full factorial design, then 3 raised to the power 3 observations you have to take. That is 3 into 3 into 3. 27 observations you have to take, and based upon the 27 observations, you have to find out the optimum conditions. If you use, can say, software, in that case, number of observations can also be reduced, and they are also part of the design of experiments. I will tell you later on. The full factorial design, 27 experiments are required, and based upon the 27 experiments, the coded values are -1, 0, and +1, and 27 observations it is written. So after taking 27 observations with 3 factors, we can get the results. This is XRD analysis of catalyst. You can see that different nodes are there, and they are characterized that, okay, this is the software we are using. Then this is the this XRD data is there for the case of calcium oxide we are using as a catalyst. Beside this one, GCMS graph is there, where easily you can find out how much area we can get. Based upon that area, how much yield we can get it. So any person with a chemical background can easily analyze those graphs. So now this is our data. After doing the 27 experiments, we can have the almost, we can say, we can have yield response for when you use a QH. Another column is for the case of calcium oxide. So you will see that lowest yield data is also there, highest yield data is also there for both the cases. So 90% of highest yield you can achieve it with calcium oxide, whereas with KOH, that is potassium hydroxide, highest yield is 97%. But we know that with homogeneous catalyst, drawbacks are there, whereas in heterogeneous catalyst, some good results we are obtaining. Now, once you have got these results, we can convert into by using ANOVA techniques, we can convert into your equation form. Because ultimately, data, if you store the data form, a huge amount of memory is consumed. Instead of this one, we can get regression analysis. We can get this particular equation, and this equation represents the graph, model for this particular observations. And if you just apply this theoretical prediction equation with respect to experimental data, in that case, we can get a graph of almost, you can see that whatever the prediction through this data is there, within the 10% our model predict quite accurately. So 10% data, if all the data is within those fitted as well as actual yield it is coming, we can consider that model is quite satisfactory. So almost more than 90% data is within 10% itself. So this is the first graph is for calcium oxide data, and the second graph is for potassium hydroxide data. Means what are the modeling we have done for both type of catalyst, it satisfied satisfactorily. Now, Minitab softwares normally, with Minitab, the graphics are available. So this equation can be utilized. This equation can be developed through Minitab, and based upon the regression analysis, the equations are developed. These are the well-known techniques in the literature. One can go through that one, how to develop the equations. Now, through those equations, what are the equations you have got it? These equations we can just graphically represent. In that case, we can see that here, this is the peak we are getting. Means this is the optimum conditions with respect to Y is the yield, and then time is on axis catalyst. So different percentage of catalyst, time, and yield, we can get this optimum conditions. Other parameters, this is for the case of almost, you can say, for calcium oxide, we are using this one. If it is Y, this is catalyst and molar ratio. This is for yield for the case of time and molar ratio. So almost in all the 3 cases, we are getting the same results to achieve the optimum conditions. And you will see that optimum conditions for the case of calcium oxide is that methanol to oil ratio 15:1, catalyst weight ratio 10.7%, and time requirement is 9 minutes, which is very, very less as compared to the conventional methods. Of course, catalyst percentage is higher because it is heterogeneous catalyst, so that percentage is higher as compared to the homogeneous catalyst. This is a 2-dimensional contours, almost, you can say, center portion, almost we can get it, okay, where we are existing. Based upon that one, for this condition, what is the composition, other things you can find out. So interpretation purpose, the optimum conditions we can analyze based upon the 3-dimensional graphs into 2-dimensional graphs. So these contours you can generate by Minitab, and Minitab has almost, can say, a huge number of applications, not only in industrial engineering but chemical engineering and mechanical engineering. This is the earlier graphs were for the case of calcium oxide, and these are the graph data for the case of potassium hydroxide, where almost optimum conditions we have generated, where yield versus time and catalyst. Here the yield versus catalyst and molar ratio, and here the yield versus time and molar ratio. So almost you can say the optimum conditions for the case of potassium hydroxide is that the methanol to oil ratio is 5.4:1 optimum condition. Catalyst weight quite reduced 0.65%, and time requirement is hardly 9.5 minutes. Whereas in mechanical string, this time requirement is around say 4 times or 5 times of this particular condition. So these surface, this response surface plots you can easily generate in softwares where well-established regression techniques you can get the answer. These are all of the two-dimensional graphs you can generate. So finally, almost once we produce the biodiesel, then we have to check whether its properties are matching with respect to the standards. So the point is that properties are flash points, cloud points, pour points, calorific value. Viscosity is a very important property. Normally, viscosity, the biodiesel is slightly higher as compared to the diesel. So all these properties and density, we have to compare. These are the commercial diesel properties. We have to compare our biodiesel properties. It is there. These are the standards available. And now in experimental study, we have achieved this one. With KOH, these are the properties. With calcium oxide, these are the properties. Now, if you compare this column with respect to our own experimental data, so almost we can see that these are the upper limits. So within the upper limits, almost you can say our results are quite satisfactory. And within the standard conditions, we are getting the results. Because ultimately, this is a very important aspect. Once we produce a biodiesel, then we have to check it with respect to properties. Without properties, we cannot say whether this will satisfy the requirement in the case of engines. So these requirements are must, and once it is satisfied, then we can say that the process is satisfactory, or application of homogeneous or heterogeneous catalyst satisfies our conditions. So comparison of performance properties are very integral part. So this is a summary of our case studies with full factorial design we have used, and based upon this one, we have achieved. These are the two columns which I already discussed, that heterogeneous catalyst we are getting, homogeneous catalyst also we are using, and based upon that optimum conditions we are finding out. Another important studies which is going under which is under process is the supercritical conditions, where autoclave we are using at the center portion, and without catalyst we can take a sample of 50 ml with alcohol plus oil, and we have a reaction, and without, in the absence of catalyst, we can convert a high temperature pressure conditions, say around more than 200 bars and 300 to 350 degrees centigrade. We can convert the reaction of alcohol plus oil can be converted into biodiesel. We have a project of GIDA, Gujarat Energy Development Association, and based upon that one, we are conducting those studies in PDPU. And we have also Center for Biofuels and Bioenergy Studies at Pandit Deendayal Patel University, and laboratory facilities are at developing stage. Now, the final aspects I will just discuss about the environmental concerns. You will see that as compared to diesel, there is significant reductions in the pollutants are there. CO 67% is reduced, soot particles also 50% is reduced, NOx and CO2 also it is reduced. NOx slightly sometimes it is improved, but the point is that with proper injector proper injector pressure, NOx can also be reduced. Normally, if you compare that conventional diesel cycle, what are the CO2 emitted in the atmosphere, that is not converted into petrol because it takes a large number of years. Whereas in the case of biodiesel, whatever the CO2 emitted, it is again absorbed by the plants, and the next cycle it is again can be converted into crop. So therefore, the combustion of biodiesel is considered to be renewable, whereas combustion of conventional petrol or diesel is not considered to be renewable because it is open cycle. Whereas biodiesel, it is a closed cycle. With every crop, again, it is the cycle will be rotated. So that is the difference between CO2 emissions of biodiesel and CO2 emissions of conventional diesel. So in biodiesel, it is a closed cycle, whereas in the case of diesel, it is an open cycle. And greenhouse emissions are quite less. B100, you can see that as compared to other methods, greenhouse emissions are very, very small as compared to gasoline, LNG, diesel, significantly almost less than half as compared to biodiesel. as compared to gasoline and diesel engine itself. So this kind of scenario almost can say biodiesel. Normally, you can say this: if you use a biodiesel in this case, Delhi and other metro cities, almost a lot of can say smog is there. So this smoke can be reduced by by encouraging the application of biodiesel and by replacing the conventional diesel. So biodiesel can help make this a scene of the past. Majority of particularly Delhi and other metro cities, the smoke is a big problem. We have applied it on engines also. We have seen that NOx formation is reduced, particulate matter is reduced, hydrocarbon is also reduced by using biodiesel. So this is a general test which we have done. Beside this one, algae can also play a very important role. Algae as a source is has a very high potential as compared to the conventional ones. So up to 70% of algae biomass is usable oils. Algae can survive in water of high salt content, means even sometimes in the sea water also one can grow the algae. And previously, earlier it was unusable, but now almost algae has a huge potential. And as shown in the right hand side diagram, this algae can produce a huge amount of oil. This slide clearly shows that as compared to other sources, microalgae, almost you can say gallons of oil per acre is very, very high as compared to the other seeds. So due to that reason, this has a good potential. And plus at the same time, the growth requirement also per hectare is very, very high as compared to the others. So algae biomass converted into biomass plus spent biomass, then other products are there and converted into animal feed and methane. So algae is the very, very valuable thing as far as the source is concerned. And using this source, normally this is algae pond where continuous rotation of water takes place, and here the captured CO2 is mixed with the water so that algae growth will be very fast. In this particular plant, almost you can say algae can be growth in a very fast. And in our country, what happens? The temperature and pressure conditions are quite conducive. If you go to Canada and cold countries, the growth is very small. Why? Because they are the low temperature countries. So minus temperature, the growth will not take place. Our country's temperature and pressure conditions are quite favorable for the growth of algae. These are in California, people are just constructing this algae growth plants, and similar type of things can also be grown in our country also. So let me almost say finish with this one. Rudolf Diesel, in his lecture in 1890, which is a recorded lecture, the use of vegetable oils for engine fuels may seem insignificant today. Because at that time, people just laughed at him, why you are trying for vegetable oils, because petrol is available. But 100 years back, he has forecast that but such oils may become in the course of time as important as petroleum and the coal tar products of the present time. Means he has already predicted that this vegetable oils will be used in the engines. And after 100 years, back to the square one, now people are thinking that this vegetable oils are the main source for converting into the engines. So that was the vision of Rudolf Diesel. Let me conclude with that one. Almost can say biodiesel can give you national security, environmental point of view it's good, public health point of view it's good, economics, a new market can give in the developing world, operation point of view it's also good, and it can help in the mankind, and energy farming is also possible by using the biodiesel. So let us pledge together to create a new dawn of green energy era, and this will be almost as a long term. Why this is important? Because it is a closed cycle. Whatever we grow, use it, and then emit it, and again carbon dioxide is absorbed. From that point of view, this is very important, and any cycle from development point of view is to be sustainable, and sustainable means it's a closed cycle. Our conventional energy sources, we are using open cycle, which is a major drawback of that particular place. So finally, let me finish this lecture with the sentence given by Yukteswar Giri: so long as you breathe the free air of earth, you are under obligation to render grateful service. So this is a very important aspect, and with this objective, I am just finishing. And if there is any query, I would be glad to answer for the same.